Hello, this is Math 2270 coming to you from the College of DuPage for summer 2020, and this is the conclusion of the lecture entitled The Cauchy-Euler Equation. Last time I left you and you were solving this problem. I hope you did solve this initial value problem, but maybe you didn't. So if you didn't, now's your chance. You know what to do. Let's see how you did. Well, first of all, you do recognize that it is a Cauchy-Euler equation because it matches the form and it's an IVP. So you first need to find the roots, and we're going to substitute x to the m in here and take the derivatives. Actually, it's not x to the m, it's x to the r the way I was doing it. And so you get two roots, and the roots, so you substitute in. This is the polynomial, it factors. And so the two roots to this polynomial are going to be 5/2 and -3. That means the general solution is y is equal to c1, that is x to the 5/2, plus c2, that is x to the -3. Now to find the constants, we're going to have to plug in to that expression and to the derivative. Here we take the derivative, we plug in, and we get two equations in, two unknowns. We solve these, and this is what c1 and c2 are. So the actual solution then is this one. Y of x is equal to 2 over 11, x to the 5/2 minus 2 over 11, x to the -3. That's an accident that the absolute value of those constants was the same. It doesn't always work out that way. Now we move to the case where we have real repeated roots. That means there's only one root, and here we're calling it m. So m1 equals m2. Well, what we're going to do is we have one solution, we're seeking a second one, so we're going to use the technique of reduction of order for the second time, maybe the third or fourth time in this course, to find another one. So what we're going to do is we're going to go through this process. This is worked out in your book, and we're going to find a second solution based on the first one, and we use the equation that we have, and we find out that that solution is going to be x to the m1, where that was the root we started with, but then that is times ln x. So the general solution then is going to be y is equal to c1 x to the m1 plus c2 x to the same m1 times the ln of x. And if you had a higher order polynomial than second degree, if m1 is a root of multiplicity k, then it can be shown that your k linearly independent solutions are going to be these. And you see there's an analogy that happens with this, and you're just raising those logarithms to higher and higher powers. So here's a problem for you to do. We want to find the general solution to this. You know what to do. Let's see how you did. Okay, so we substitute x to the m in here. We take the derivatives and we look at these again. I am using r's instead of m's, but this is what we get for our auxiliary function equation, and we can solve this. This is r minus 4 whole squared. That means r equal 4 is the root. So the general solution, y of x, is going to be c1 x to the 4th plus c2 x to the 4th times the natural logarithm of x. We have one more case, and that's where we have conjugate complex roots. So what we're going to say is we have m1 is equal to alpha plus I beta, and we have m2 is equal to alpha minus I beta. And so, and you see what we're really doing is we're starting with these things as being complex exponents, but then we're going to use Euler's identity and much of the techniques that we used before when we got the conjugate complex roots, and we find out that y1 is going to be x to the, and that is going to be x to the alpha times the cosine of, and the argument of the cosine is beta ln of x. And we find out that y2 is going to be x to the alpha times the sine of beta ln x, and this constitutes a fundamental set of real solutions. So the general solution is a linear combination of those. And again, you see we factor out the x to the alpha and tend to put the constants inside being multiplied by the sine and the cosine. So here is a problem. You're to find the solution to this differential equation. You know what to do. Let's see how you did. Okay, so we're plugging in x to the m here, and we end up with this, actually x to the r, I'm sorry. We plug it in and we get these, this is your auxiliary equation. And if you use the quadratic formula, this is going to be minus 1 plus or minus the square root of 3i. So it's going to be x to the minus 1. And the square root of 3 is going to be the multiplier for the natural logarithm in the argument of both the cosine and the sine. So the general solution is then going to be y of x is c1 x to the minus 1 cosine square root of 3 ln of x plus c2 x to the minus 1 sine of the square root of 3 ln x. Now, sometimes you're interested in a point away from 0, and so sometimes you're looking at a problem where it looks like this. This is x minus x naught squared. So you see the singularity or the issue happens at x0, and so what we're going to do is we can do, well, there's a number of things we could do, but you see we can talk about doing this at a different point. We could either substitute a variable, or we could just use x minus x naught without doing a substitution, and it's going to work the same way. The structure of this is a Cauchy-Euler equation, okay? And the point that we're worried about now is the point x0, but that would correspond to the original Cauchy-Euler we talked about at x equal to 0. Now, what I said is, you might say, well, what happens if it is negative? Well, you can do that too. So here is the solutions in this general case for any interval not containing the point of interest x equal a are. Here we have R1 and R2. That's if they're distinct roots. So this would be the solution away from the point A. This would be the solution where we have a repeated root. It is R is a double root. And so we would give this as our fundamental solution. And down here, and by the way, this is lambda plus mu I is what's being talked about here. But if your root is lambda plus or minus mu I, this is what you get for your solution. Where all those roots that we were talking about up here were roots to whatever this equation is, your auxiliary equation. So here is example 4. You want to find the solution to this on any interval not containing x equal minus 6. So if you look at this, you see what we have is this is x minus a minus 6. This is x minus a minus 6. You know what to do? Let's see how you did. Okay, so you get the roots by substituting in here. And you get 3r squared plus 22r minus 16. That factors. You get r1 is this and r2 is that. So the general solution, which works as long as you're away from the point x equal minus 6, is this one. And there's the 2/3 exponent, and there is the minus 8 exponent. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of others. God bless.